Hello everyone, my topic for ISC presentation is Electrothermal Thruster and my group members are Sejal Tate and myself as Muskan Attar. So now talking about the Electrothermal Thruster in next slides. The content we are going to learn in this presentation is what is Electrothermal Thruster, what are its types, like resistojets and arcjet are the types of electrothermal thrusters. Moving towards the next slide. Also, you can see the diagram which is downwards here. This is a diagram of electrothermal thruster. As I have told earlier that electrothermal thrusters are broadly divided into two types like resistojets and arc jets. I will discuss about the resistojets. Now talking about the first resistojets. Like here the first point is the propellant gas is heated by making it come in contact with electrically heated solid. What does it means? So this point explains that, like I will give you an example. Imagine you have a special rocket like a fuel like a gas. To make it really hot, you can make it touch a surface that heats up when you pass an electricity through it. When you pass electricity through it, it's like when you touch a hot stove and warms your hand, but in the case it's a rocket fuel getting hot by touching a surface that's heated up by electricity. The super hot fuel and then turns into a powerful gas that shoots out the rocket, making it go forward, or it allows the rocket to move forward. Now, the second point of this slide tells us that when we want to see how well electrothermal rocket engines work, we use certain measures like thermal coefficient. This tells us how effective the engine is at producing thrust or forwarding push. Characteristic velocity. We can denote it as C star. This is a measure of how fast the gas is expelled from the engine, an important factor in propulsion. Even you third point is like specific impulse is also one of the major important factor. This is another way to measure how efficiently the engine is using its fuel to produce thrust. It's like checking how far you can go with a certain amount of gas in your car. Then then last point is like efficiencies. These are the measure of how well the engine converts into energy like electricity into useful thrust. It's like checking how much of the electricity you put in is actually used to propel the rocket forward. Then the third point which I have written in the slide is like the characteristic velocity depends only on the molecular weight. What this statement means, like molecular weight, this is like the average weight of a molecules in the rocket fuel. Lighter molecules contribute to the higher characteristic velocity. Specific heat ratio, this is a measure of how much the gas can be heated. If the gas can absorb a lot of heat, it can generate more thrust, contributing a higher characteristic velocity. Temperature of the propellant gas, to the hotter the gas, the faster it can be expelled, leading to the higher characteristic velocity. In the simpler words, the speed at which the rocket can shoot out its propellant, characteristic velocity, depends on how heavy the molecules are, means like how heavy the molecules are and how well the gas can be heated and how hot the gas is. These factors could crucial These factors are crucial for the rocket's performance, whether it's an electrothermal or a traditional chemical rocket. Now, let's talk about the fourth point, which is mentioned in the slide. All electrical resistive power transfer to the propellant cannot be converted into thrust power. The electrical energy can be lost due to, means like the energy electrical energy can be lost due to the stake currents or ohmic resistance, heat losses, non-axial components of the exhaust. It means that when using electricity to heat up rocket propellant, not all the energies goes into pushing the rocket forward. Means like some energy is expelled, or we can say that it is lost. Some is lost due to the resistance escaping as heat and inefficient direction of the propellant, making the propulsion less effective. Now you can see the thrust equation or efficiency of thrust here. It explains that the equation provides means like thrust efficiency, which is denoted by eta T of the rocket propulsion system. Let's break down these equations. Eta T means the efficiency of propulsion system. M is the mass flow rate mass flow rate um, flow rate of propellant, how much and propellant is used in a unit time. VE is the exhaust velocity of the propellant, how fast the aircraft expelled. PJ is a power supplied to the rocket or the rate at which the energy is added to the propellant. VI is initial velocity of the rocket. F is equals to thrust produced by the rocket. ISP is the specific impulse of the rocket, a measure of how efficiency the rocket uses the propellant. G is acceleration due to gravity. Now let's explain the equation what you can see in the slide. NT is a MVE square. This part of the equation relates the kinetic energy of the expelled propellant M into VE square to the power supplied of the rocket PJ. It essentially tells you how efficiently the supplied power is converted into the kinetic energy of the of the expelled propellant. Second, NT is equals to M into VE square upon 2 VT. This part expresses the efficiency in terms of initial velocity VI of the rocket. It indicates the propulsion of the kinetic energy of the expelled propellant compared to the initial kinetic energy of the rocket. Third is like NT is equals to F ISPG upon 2VI. This part relates the efficiency of the thrust F, specific impulse ISP, and the acceleration due to gravity G. It gives you an idea how efficiently the rocket is using its thrust in the presence of gravity. In summary, we can say that the equation provides different ways to express the efficiency of a rocket propulsion system, considering factors like power inputs, velocity, thrust, and specific impulse and gravity. Each term of the equation contribute to the understanding, means like how efficiently the thrust or the rocket converts energy into the propulsion. Now the further slides of this presentation will be explained by my partner Sejal Tati.
Hello everyone, this is Sejal Tate. As my partner Muskan Attar explained about the types of electrothermal thrusters, she explained the first type of electrothermal thruster, resistor jets, and I will explain about the arc jets. So the limitations of the electrothermal rocket to have higher specific impulse can be overcome by releasing the heat to the propellant gas at higher temperature using arc discharge. Of course, the high temperature and high pressure gases are accelerated in supersonic speed by expanding in a nozzle as in a chemical rocket. Such a kind of thrusters are known as arc heating thrusters or arc jets, in which the electrical energy is converted into thermal energy by producing an arc. The typical arc jet consists of anode and cathode and CD nozzle. It must also contains both power supply and propellant feed systems. Both anode and cathode are generally is made in the shape of nozzle that can serve as nozzle for expansion of propellant gas. A steady DC voltage is to be maintained across the anode and cathode using a suitable power supply system. The current can be changed depending on the propellant flow rate. In order to initiate the arc, higher voltage as compared to steady operation voltage is to be supplied to ensure breakdown of cold gas. The current passes through the ionized gas adjacent to the cathode. The arc discharges from the tip of cathode, forming an arc column. The maximum temperature occurs in the region of arc core in an arc jet thruster because energy input to the propellant occurs in the narrow narrow thrusters because energy input to the propellant occurs in the narrow thrusters region of smaller diameter laminar flow within the throat of nozzle. Hence, the hot gas at the core of a arc must mix quickly with cold propellant gas, either with help of creating turbulence or vortex in the propellant flow. Generally, high current arcs are inherently unstable as the ions are affected not by the electrical field but also the magnetic field caused by motions of ions themselves. As a result, arc may break down into a number of columns forming pinches and wiggles known as pinching effect that may reduce the energy transfer to the propellant gas. In the case of arc jet thruster, almost half of the electrical energy is lost to the jet, while 10% to 20% electrical energy input is also lost in the form of heat losses. As a result, a typical efficiency of arc jet thruster ranges from 30% to 40%, which is much lower than an electrothermal thruster. However, it is preferred over the electrothermal one as the propellant gas can attain higher temperature in the range of 4000 to 5000 Kelvin because higher electrical energy can be transferred during the formation of arc due to direct interaction of electric current and propellant. As a result, exhaust velocities in the range of 7500 to 20,000 meter per second can be achieved with enhanced specific impulse. Generally, the thrust to power ratio of arc-jet thruster is around 6 times that of the resistor jets. But the power supply unit for arc jets is quite complex and bulky as compared to of the electrothermal thrusters. Several arc jets are being used routinely as station-keeping thrusters. As in the case of resistor jets, the catalyst decomposition of hydrazine can be used as an arc jet to further augment specific impulse. This is known as chemical arc jet thruster (CAJT). Liquid hydrazine is decomposed catalytically into gaseous products which enters the arc and at around 1000 Kelvin, gas temperature subsequently the heat transfer of this hydrogen gas can enhance product gas temperature and results in higher specific impulse. So this is all about the electrothermal thrusters, their types, resistor jets and arc jets, and here is the end of our PPT presentation. So thank you.